Good morning, Maranda. Today I am going to teach you about topic strength of materials. In strength of materials, today I am going to cover about stresses, different types of stresses, and elastic constants. What are elastic constants? Okay. The topic today is about strength of materials. Firstly, I am going to teach you about stress. Before going into the topic, the strength of materials or mechanics of solids or mechanics of deformable bodies. These all come under same name, strength of materials only. What is what does the strength of materials deal? Is nothing but, suppose you take any structure, any building or any structure. There are various kind of environmental forces like earthquake forces and wind forces, and it's also self-weight force. Self-weight will be there, loads will be there, human beings will be surrounding it on it, and these are the forces. And the structure is made up of small deformable elements. So it is a summation of structures and they summation of all those small little elements which are deformable elements. So in strength of minerals we study whether all the deformable elements can withstand the load they are getting on it. And mainly three S's are deal in the strength of minerals. One is strength, and another is stiffness, and another is stability. The strength is nothing but it can withstand that much of load or not. Stiffness is nothing but there will be not much more deformation. Stiffness is nothing but load per unit deflection. And stability, it will be stable. It will not deform due to the loads. These all three S's we study in the strength of materials. And now I am going to teach you about like stress. Not only the building structure, we can teach the bridge structure or any other structure. It will have in bridge structure we have additional moving water load. So we have to calculate that moving water load in design also. Okay, first stress. Stress is denoted by symbol sigma. Stress is nothing but resisting force per unit area. Now what is meant by resisting force? Resisting force is nothing but, suppose you take an element subjected to a load P. This is an equilibrium condition. Equilibrium condition is nothing but, according to the Newtonian laws of mechanics, there are, for a body to be in equilibrium, there are three equations. One is sigma Fx equal to 0, sigma Fy equal to 0, and sigma Mz equal to 0. These three are equilibrium equations for 2D frame. Generally for 3D frame, 3D or 2D nothing but you can see here x-axis, y-axis, z-axis. Z-axis, x-axis, y-axis, this both is in the 2D plane. Z-axis is nothing but facing you. That is the z-axis. That is the three-dimensional axis. Now you can see in 2D, that means only in xy plane, these three equations are required to solve any structure. Equations to maintain the structure in equilibrium. These are the equations we need. For 3D, we will use 6 equations like sigma fx equal to sigma, sigma fy equal to 0, sigma fz equal to 0, sigma mx equal to 0, sigma my equal to 0, sigma mz equal to 0. For 3D frame or space frame, this is for plane frame. Suppose here, if you cut the number from here, you can see that force will be P and resisting force will be R. I am cutting the member here. To maintain equilibrium condition, that means to sigma fx equal to 0, P equal to R. This R is known as internal force developed by cutting the member to balance the external force. This is nothing but a free body diagram. Free body diagram is nothing but removing the supports from the diagram and represent in an equilibrium position. So this is nothing but resisting force per unit area. And what are different types of stresses? Types include, one are direct stresses and second one is indirect stresses. Stresses is divided into two types. There are direct stresses and indirect stresses. And in direct stresses, again there are two types: normal stresses and tangential or shear stresses. And indirect stresses, there are again two types. One is bending stress and second one is torsional stresses. You can see here stress, types of stresses, direct and indirect stresses, normal, tangential, bending, shear. Now I am going to explain you each terminology and why it occurs and where it occurs. This normal stress is nothing but if you take a member which is subjected to the load P, and normal stress is nothing but normal force. Normal force to this is the cross section area. Force by cross section area. This is normal stress. And tangential or shear stress means if you take a member subjected to a force P, that F is along this plane, along the topmost plane. Shear stress is nothing but shear force by shearing area. Shearing area nothing but this whole area will become as a shearing area. Shear force upon shearing area. And the units I forgot to mention are like Newton per meter square. Force, resisting force nothing but units newtons, and area is nothing but meter into meter, so meter square. Units of stress. This we term as Pascal. So here everything Pascals. Stress is nothing but Pascals. Stress is nothing but units Pascals. And bending stress. This bending stress and torsional stress. These two are indirect stresses. This bending stress is due to in beams. Say a beam is subjected to transverse load. First of all, I will tell you what is meant by beam. A beam is a horizontal member which is subjected by transverse loadings. Due to this transverse loading, there will be a bending moment. Like bending moment. Now see, what is a beam and what is a bending moment? Bending moment is nothing but always beam. This is the longitudinal axis of the beam. This longitudinal axis of the beam, there will be transverse loading. Due to this transverse loading, the beam bends. Like the beam will bend like this. It will bend like this. Arc of a circle. Or due to the bottommost loads, it can bend like this. It is called hogging moment. Because of these two things, because of this transverse loads, the beam bends now. By bending is nothing but you see this vectorial axis diagram. The beam is bending like this. So the vectorial notation will be in the z axis. So beam is nothing but in the beam, the forces, the moments, the vectorial direction of forces and moments will be in the z direction. That is perpendicular to the axis of the member. In a beam, I am repeating you, in a beam, the vectorial notation of forces, moments will be perpendicular to the axis of the beam. This is not the longitudinal axis. You can see this is in the x plane, say. Due to this moment, we are getting a vectorial direction of mz. So, in torsion, you can see a circular shaft subjected by a torque T. Due to this torque, there will be torsional shear stresses. Torsional shear stress, and the vectorial notation will be, and the vectorial notation, see, keep your hand like this in the shape of the shaft and rotate it. This is not a torsion. This is bending. The beam is bending like this, and due to the torsion, the beam is bending like this. So the vectorial notation will be along the axis of the member only. The vectorial notation, this is called vectorial notation, will be along the axis of the shaft only. This is known by, this is due to this there will be torsional shear stress developed. Due to this torsional shear stress, there will be distortion in the cross section of the shaft. Due to this bending moment, there will be bending stresses. We will get bending stresses. Due to this torsion, we will get torsional stresses. On the next topic is about elastic constants. In the elastic constants, we study about 4 elastic constants: Young's modulus, rigidity modulus, bulk modulus, and Poisson's ratio. This Young's modulus is nothing but stress is directly proportional to strain, always. Because while doing a mild steel, we will take and we will keep it in universal testing machine. We will get a graph like stress will be proportional to strain up to proportionality limit. So here stress equal to I will write as constant as E and strain. Therefore, E equal to stress by strain. And second, similarly, this shear stress is directly proportional to shear strain, and G equal to shear stress by shear strain. And similarly, K, pressure upon volumetric strain. And Poisson's ratio, last one I will be telling you about Poisson's ratio. Poisson's ratio is nothing but ratio of lateral strain by longitudinal or linear strain. And the values of the Poisson's ratio lies between 0 less than 0.5 to 0 to 0.5. Values of Poisson's ratio develop. And finally, at last, I am going to teach you about the relations between these elastic constants. This is very important topic. You can see here E equal to 2G into 1 plus mu. E equal to 3K into 1 minus 2 mu. E equal to 9kg by 3K plus G. These are the three important relations between these elastic constants. This is the elastic constants. E is nothing but Young's modulus, G is nothing but rigidity modulus, mu is nothing but Poisson's ratio, and K is nothing but bulk modulus. Okay, these are the three. By combining these three elastic constants, we can get these three important equations. These are very important. Okay, thanking you.